Hello, and welcome to this second session on fMRI data analysis within the Neuroimaging Lecture at the Berlin School of Mind and Brain. So today we are discussing statistical analysis of fMRI data, which most often operates using the general linear model. Once again, I will give a short introduction, which is mostly a recap from last week. Then we will build our first simple linear model for the experimental paradigm which we are modeling. We will extend this approach to general linear models, and we will then, in the fourth section, know or learn about a few problems related to specifically modeling fMRI and to which GLMs have to be adapted. And then I will close with an outlook on what else can be done based on the general linear model. Okay, so this is our overview of fMRI data analysis. Last week, we learned about preprocessing, so everything that's in the red box on the left. And today, we are assuming that we have preprocessed fMRI data, a preprocessed fMRI time series, which is ready for statistical analysis. So we will learn about everything that's in the blue box on the right today. Once again, I will use SPM version 12 running on MATLAB to demonstrate how this GLM-based first level fMRI analysis can be performed. This is how SPM looks like running on MATLAB. And once again, I just want to mention that there are alternatives to SPM for GLM analysis. I'm here giving you the routines for GLM analysis from each package that I also mentioned last week for preprocessing. So in AFNI, the routine is called 3D deconvolve, and you will learn later why it's called deconvolve. It has to do with the hemodynamic response. Then there's FSL feed from the FSL library. In PreSurfer, this is called MRI GLM fit. And in NiLearn, there is the submodule GLM. NiLearn is a Python package for machine learning-based analysis of fMRI data, which also includes a routine for the general linear model. Okay, so with that, we are back at the fMRI dataset that I'm using as the running example in my two lectures. And today we are actually talking about the experimental paradigm. So what specifically subjects were viewing and doing in this experiment. So in this experiment, subjects were presented with photographs showing indoor and outdoor scenes. And these photographs were either new to the participants at the time of presentations, so novel images, or they were pre-familiarized with the subjects by showing them to the subjects before the experiment repeatedly, 10 times or so. These are here called master images. Then in a this was the encoding session, and then in a retrieval session, subjects were presented with all the novel images from the learning part, as well as a couple of new images. And they were then asked to rate each image on a Likert scale ranging from 1 for this item is definitely new to me, up to 5 for I've definitely seen this item before. So this is to gather data about some kind of encoding success or learning process happening in the subject. So the goal today will be to build a model for describing the fMRI data measured during the learning part of the experiment, because this is where fMRI was measured, but partly dependent on what was happening during the retrieval part of the experiment. We will see how that works later on. So, simple linear model. Let's get back to our experimental design and have a look at it in more detail. So we don't need this and we don't need that. And please, for the moment, ignore the indoor-outdoor dimension. Yeah, so ignore that the pictures shown to the subject were either indoor or outdoor images. Then we have two experimental conditions, one consisting of the presentation of novel images and one consisting of the presentation of master images. So these two experimental conditions can be called experimental condition 1 and 2, or condition of interest, because we want to know what's happening during the presentation of novel images, and control condition, relative to which we want to contrast the novel images. Okay, so because we have designed the experiment and we have programmed the stimulus presentation, we know at which point in time the subject was in which experimental condition. Yeah. So this can be visualized using such stimulus functions, which are shown here in red. These are just functions which are 0 when this experimental condition is not active, and 1 when the subject was in this experimental condition. Very straightforward. So then we are taking our pre-processed functional image time series, and we are focusing on a single voxel. Could be the voxel which is here highlighted using the red crosshair. And from this voxel, we extract the value at each successive functional MRI scan. This then gives us the Bolt signal, so a measurement of the measured brain activity over time, which is here shown as a vertical plot. This signal from this voxel then enters model specification. The model is being estimated. Based on the estimated model parameters, we perform statistical inference, and this then gives us these nice thresholded statistical maps, which we see in the bottom right. This is being done for each voxel separately, which is why this is called voxel-wise time series analysis. So as an output from pre-processing, we also have a measured Bolt signal, simply because we have measured and then pre-processed it a bit. And the goal would now be to obviously relate the measured signal in the upper part in blue with the hypothesized signals in red given by our stimulus functions. So very naive first model for the measured Bolt signal could look like this. We say that the measured Bolt signal, here given in blue on the left, is equal to variation due to experimental condition 1, weighted by some scaling factor, beta 1, plus variation due to experimental condition 2, again weighted by some scaling factor, beta 2, plus some baseline level of neural activity, here called beta 3, plus some noise, which is also in the signal and which lets the signal deviate from our a priori expectations. This is here shown in blue on the right. So this model could be summarized using the following formula. And in this formula, Y is called the Bolt signal. X1 and X2 are called the condition regressors. X3 is called the implicit baseline or constant regressor because it does not change its values. And epsilon is called the vector of errors or noise. This is, of course, a naive single voxel model because it ignores several important properties of the Bolt signal. For example, there is the hemodynamic response, but we will come to that later. So now the question is, how do we calibrate these betas, the scaling factors in our equation, beta 1, beta 2, beta 3? So obviously what we want to achieve is that we want to well explain the measured signal using our statistical model. So we can just pick some parameters, some values for the parameters better, and then see how the modeled signal in red compares to the measured signal. And of course, there will be situations when the modeled signal is somewhat too small, here given on top, and other situations in which the modeled signal will be too large compared to the measured signal here given in the bottom. And we are seeking those parameters, the optimal betas, that we give the best fit of the modeled signal relative to the measured signal. This is what's here shown in the middle. Once again, this is a naive view of parameter estimation because it's more a heuristic for parameter estimation rather than a principled mathematical approach, which we will have a look at later on. So we will see how it works more precisely. So now that we have estimated those betas, which are also called the regression coefficients, we can have a look at the estimated coefficients. So we denote the estimated coefficient of the ith regressor as beta hat I. So this hat always stands for estimated. And we can ask ourselves what we can conclude from the estimated beta values. So we could, for example, have obtained the following values, beta 3 being around 100, so that the baseline signal is around 100, beta 1 being 9.82, beta 2 being 5.07. And then what we could do is we could subtract beta 2 from beta 1, which is 4.75, and this is larger than 0, so we could conclude, therefore, experimental condition 1 elicits larger activity than experimental condition 2. Therefore, there's a positive effect of novelty on the signal. So we see a higher increase of activity during the presentation of novel images than during the presentation of master images. Once again, this is a naive way of statistical inference because it pretends one can ignore the noise that is also in the signal when assessing whether something is statistically significant or not. And we will also see how that works precisely and how the noise is integrated into the equation later on. So we have now introduced a very simple linear model for the present data set. And the question is, how can we generalize this to any context in which we might acquire task-based fMRI data? So the idea is to take the two-condition model, which we have specified here, and generalize it to multiple linear regression with an arbitrary number of predictor variables and an arbitrary number of experimental conditions, for example. Additionally, we will need to make some assumptions about the errors or the noise in the data, because otherwise we cannot make any statistical inference. So these considerations lead us to the general linear model, or the GLM. And the GLM decomposes the bold signal measured in a single voxel, which is here given as the n/1 vector y on the left side, into variation coming from experimental conditions and potential confounds, which are collectively referred to as the design matrix X, weighted by some regression coefficients, beta, which is a p/1 vector, plus some noise, epsilon, which is always in the data and which cannot be decomposed using our model. So this GLM approach is very flexible because new predictor variables or new experimental conditions can just be added as more columns to the design matrix. Yeah? So we can easily adapt our model to new experiments or to model a given experiment in another way. Ideally, the design matrix should embody all the available knowledge about experimentally controlled factors and potential controls. So everything that you know about and that you have an assumption about has influenced the bolt signal during your function MRI measurements should be in the design matrix. Here in the GLM, the errors are assumed to be independent and identically distributed. This is also called the IID assumption, according to a normal distribution with a mean 0 and an unknown variance, which is called the noise variance, and which also has to be estimated. So this is the display of the linear model that I've used so far. I've here represented the condition regressors and the measured signals as vertical line plots, if you want. And this is a rather unconventional display of the GLM for fMRI because in software packages, this is usually displayed like this. So you're usually seeing the design matrix as some grayscale color plot showing you the structure of the regressors, which in this case are just 3. And these 3 columns would correspond to the 2 condition regressors and the constant regressor that we already saw earlier. There is an interesting geometric perspective on the GLM, which also allows us to come up with first simple approach for parameter estimation. And this geometric perspective is as follows. So let the design space be the portion of multiples of the multidimensional space, which is spanned by the columns of the design matrix. So we assume the columns of the design matrix to be vectors, which are spanning some space in multidimensional space. And this is the space of all points that can be reached by multiplying the design matrix with some arbitrary regression coefficients. Yeah? So we can take a beta 1 and a beta 2, multiply them with x1 and x2, and this will then bring us to some point on this design space. Then we have the measured signal, which can also be represented as a vector, and which will usually not be on the design space. So if the measured signal was on the design space, there would not be any noise in the signal. But there is noise in the signal, so the measured signal is usually not on this plane spanned by the column vectors of the design matrix. So then the question is, how do we choose our model signal? Our model signal must be on the design space because it's a product of the design matrix and some estimated regression coefficients. And here the idea would be to pick that point on the design space, which leads to the shortest distance between the hyperplane spanned by the design matrix and the actually measured signals. So in this case, the vector of residuals will be orthogonal to the design space. So the point on the design space from which we can draw a vector to the measured signal, which is orthogonal to the design space, will be the model signal and will therefore specify the estimated regression coefficients. We can use this to come up with an equation for parameter estimation, which is called ordinary least squares. The objective here is to minimize the sum of squared errors. And as you can imagine, minimizing the sum of squared errors is equivalent to finding the shortest distance between the design space and the measured signal. So we can take what we have just learned about the geometric perspective and say that the vector of residuals must be orthogonal to each column of the design matrix. And if two vectors are orthogonal, you probably remember that their product must be 0. So this follows from the geometric perspective on the GLM. And then we can simply insert the difference between the measured and the modeled signal, because this is the vector of the residuals, into the equation. And then we can multiply out and rearrange for better head, so the estimated regression coefficients, and obtain a very elegant equation which says that the estimated optimal regression coefficients are equal to the covariance of the design matrix X with the measured signal Y divided by the covariance of the design matrix itself. So if you want to remember one single equation from this lecture, it should be this equation, the equation for obtaining ordinary least squares parameter estimates. X transposed times X, and then the inverse of that times X transposed Y. So once we have estimated model parameters, we can use them for statistical inference. And the way of statistical inference I want to introduce here is contrast-based inference. There are two types of contrasts, T contrasts and F contrasts. T contrast is specified by a contrast vector C, which has the same size as the vector of regression coefficients. So it's a P by 1 vector, where P is, for example, the number of experimental conditions, or more generally, the number of columns in the design matrix. This is how a T contrast could look like. So we have a contrast vector C, which places one weight on each column of the design matrix. So in this case, we have a +1 on the first condition, and a -1 on the second condition, and a 0 on the implicit baseline, or the constant regressor. And if we now multiply this contrast vector with the vector of regression coefficients, the result will be the difference between beta 1 and beta 2. So beta 1 minus beta 2. This means that the research question implicated by this T contrast is there a difference between the first and the second regressor? And if that would be the case, this would be a yes to this research question. An F contrast is specified by a contrast matrix C, which can also be a contrast vector in the case that this Q here is just 1, but it can also be a matrix. So here's an example where the F contrast is a matrix. We have 2 columns in this matrix, and one is placing a weight of 1 on the first condition, and one is placing a weight of 1 on the second condition. So if we multiply this with the vector of regression coefficients, the result would be a new vector containing only beta 1 and beta 2. So the research question asked by this F contrast would be, is there an effect of the first regressor, or is there an effect of the second regressor? And if either of them is the case, this would be a yes to this research question. So here's a more precise mathematical treatment of contrasts. In T contrasts, the quantity of interest is the contrast value, which is a scalar, a real number. So that's the product of the contrast vector with the estimated regression coefficients. And our null hypothesis when using a T contrast will be that this contrast value is 0. So in the case of the regressor, which is shown on the right, that there is no difference between experimental condition 1 and 2. The alternative hypothesis will be obviously that the contrast value is not 0, or that it is larger than 0. Under the null hypothesis, we can then derive that this test statistic here shown in the bottom follows a t-distribution with degrees of freedom specified by the number of scans and the number of regression coefficients, n minus p. Here's the precise treatment for F contrasts. So in F contrasts, our quantity of interest is the vector of contrast values. This can be a scalar number if the contrast matrix has just one row. Otherwise, it is a vector. And if it is a vector, the null hypothesis is that all entries of this vector are 0. So in the case of the contrast matrix shown on the right, this would mean that activation due to the first experimental condition is 0, and activation due to the second experimental condition is 0. The alternative, the negation of the null hypothesis, would therefore be that at least one contrast value is non-zero. So either there is an activation of due to the first experimental condition, or an activation due to the second experimental condition, or both. Then, under the null hypothesis, this test statistic here in the bottom, the F value, follows an F distribution where the degrees of freedom are once again specified by the model parameters n, p, and q. So what does it all mean? Why is it useful to set up T and F contrasts? And what do we gain from these test statistics being distributed according to some distribution? So the consequences for statistical inference is that we can now use those test statistics, T and F values, to reject the null hypothesis if they have appropriate values. So here on the left, this gives us the distribution of the T value under the null hypothesis, shown in black. And if we then take the actually observed T value, here shown in blue, we can calculate the probability of obtaining a T value which is as extreme or more extreme than the actually observed one. This is here shown as the red area under the black curve. This area is called the p-value. And if the p-value is sufficiently small, that is smaller than our significance level alpha, which for example is 0.05, then we reject the null hypothesis and accept the alternative hypothesis that there is a significant difference between the experimental conditions, for example. The same can be done for F contrasts, obviously. So on the right, we see the distribution of the F statistic under the null hypothesis as the black line. And once again, we are calculating the probability of obtaining an actual F value, which is as extreme or more extreme than the actually observed test statistic. This is the area shown in red. This is the p-value, and if the p-value is smaller than our significance level, then we can reject the null hypothesis and, for example, conclude that there is activation in at least one of the experimental conditions. Okay, so this is it for the general mathematical apparatus behind general linear models. And in the second half of the lecture, roughly, we now want to look at a few properties that are specific to fMRI signals and which need to be accounted for when making fMRI signals, when making general linear models fit for fMRI data analysis. So the first of these problems is the existence of low frequency drifts. As I already explained last week, there are slow trends or drifts in the measured fMRI signal, which are most often due to scanner properties and which can make model estimation less accurate, obviously, if they are not being accounted for. The solution here is that we build a discrete cosine transform basis set. So in the bottom right, this shows you the temporal DCT set and regress it out of the signal. This is called temporal filtering. So here's how this could look like. On the left, we are seeing the pre-processed signal, which includes a linear and a quadratic trend. And in the middle, we can see the DCT matrix embodying several temporal frequencies of how the signal could be changing. You can see that the frequency of signal change is increasing when moving from one DCT regressor to the next. And then we calculate the residual forming matrix of this DCT set, which is here given by this matrix R0, and right multiply it with the preprocessed signal. And this then gives us the temporally filtered signal where the temporal trends have been largely removed. And this will be the step for everything that follows. So for all the subsequent GLM analysis steps. In SPM, when you want to set up a first level statistical model and specify temporal filtering, you choose the module fMRI model specification. There you can enter the preprocessed fMRI scans, and you are choosing a high pass filter cutoff value, which is here 128 seconds. And this determines which frequencies are removed from the signal or kept in the signal. So in this case, frequencies with a period length longer than 128 seconds. It's pretty long because it's more than 2 minutes. Or in other words, frequencies which are smaller than 1/128 Hertz will be removed from the signal using this temporal filtering approach. Okay, next problem is the hemodynamic response. So as you can imagine, fMRI signals do not have this rectangular shape, which we assumed them to have when using those rectangular stimulus functions in the beginning when we were setting up our first simple linear model. In fact, the hemodynamic response of a brain region relative to simulation is slow. It's very delayed, and it has the shape that is given on the bottom right. So the solution here will be that we don't use the stimulus functions, but the stimulus functions are convolved with the hemodynamic response function, which is given on the bottom right, to yield a more realistic prediction of the fMRI signals that we have measured. So the hemodynamic response peaks at around 5 seconds after stimulus onset, and then it has a large post-stimulus undershoot between 10 and 20 seconds, and the convolution operation works as follows. So we have our stimulus functions on the right. These are once again the 2 experimental conditions. And we then take the hemodynamic response function from some software package, for example, SPM. In SPM, the canonical HRF looks like this. And then we apply a convolution operation between the rectangular stimulus function and the hemodynamic response function. And this gives us the actual regressors, where you can see that the activation due to the experimental condition has somehow been smeared out temporarily using the HRF. Here's a visualization of convolution taken from Wikipedia, and maybe the bottom filter given in blue is more similar to our hemodynamic response function. So the red could be our stimulus functions. And then you can see that those stimulus functions are some kind of moved over the filter using which we want to convolve them. And this gives us an aggregated signal over time, which we use for modeling the measured fMRI data. If you want to, in SPM, implement HRF convolution, you don't have to do it yourself. You can just, during model specification, select a MAT file, which is containing the names and onsets and durations of your experimental conditions. This will be used to automatically generate stimulus functions, and then the stimulus functions are convolved with the HRF that you choose. Here we choose the canonical HRF for convolution with the stimulus functions, and this then produces those HRF convolved regressors in the design matrix. So this is how our design matrix looks like. For our experiment, please only have a look at the first 3 columns at the moment and ignore what comes afterwards. So the first column corresponds to the HRF convolved regressor for the novelty condition, and the third regressor corresponds to the HRF convolved regressor for the master images. I will tell you about the second regressor later on. And here we have now specified a t-contrast comparing the novelty against the master images. And this then gives us a statistical parametric map, which is showing us regions where this contrast is positive, if you want. And this includes a large number of regions in the visual cortex, because this is a visual incidental encoding paradigm, including, I think, parahippocampal place area, which is probably reacting to those scenes shown on the photographs. Next problem, residual movement effects. So here the issue is that although we have performed spatial realignment during preprocessing, there are still some movement artifacts in the signal, so it's not possible to fully remove the effects of motion from the measured signal, especially at the tissue boundaries. So where, for example, the gray matter encounters with the CSF. The solution here is very simple. We just take the realignment parameters that we obtained from spatial realignment during preprocessing as regressors into the design matrix of the GLM. So on the left, we have our design matrix consisting of HRF convolved condition regressors plus the implicit baseline. And then we take the head motion parameters, the translations and the rotations, and just add them as additional regressors. And this then gives us the full design matrix for data analysis. In SPM, if you want to account for residual movement effects, you simply take the text file containing the head motion parameters created during realignment and here enter it into the multiple regressors field. If here I have specified an F contrast over the head motion regressors, this is also called an omnibus F test because it tests whether there's an effect of any of the motion regressors. And in the bottom, you can see the boxes where such an effect exists. And you can see that especially at the tissue boundaries between the gray matter and the white matter, or the gray matter and the CSF, we still have those residual movement effects, which can be explained using the head motion parameters, and then further reduce the noise variance in our signal. Next problem, serial autocorrelations. So in fMRI, consecutively measured scans are not statistically independent, which means that the assumptions which we're making earlier about independent and identically distributed errors is violated. And fMRI time series have some serial correlations. That is, adjacent scans tend to be correlated to each other. This is in part due to physiological properties and in part due to the hemodynamic response, which is rather slow. The solution here will be to fit an autoregressive model of order 1, which is also called an AR1 model, to the measured signals in order to account for serial autocorrelations. So just to give you a little bit of background, the sphericity assumption is equivalent to assuming that errors are independent and identically distributed. And this in turn is equivalent to the error covariance being a scalar multiple of the identity matrix. This is being shown on the left. In this case, the covariance matrix of the errors could look like this. So you have a spherical shape and equal variance in any direction. So there are different ways how sphericity can be violated. So on the right, we have examples for non-sphericity, which include non-identity and non-independence. So in non-identity, the variance for the different directions is different. This would in fMRI mean that we have different variance for different time points. And in non-independence, which is the case which we are targeting here, the shape of the errors is, or the shape of the error covariance is not spherical but elliptical, and this ellipsis has some direction in space so that adjacent errors tend to be correlated with each other, positively or negatively correlated. So the solution here will be that we cancel our IID noise model and replace it by an enhanced noise model in which we don't have an identity matrix in the assumption there, but another matrix V, and this matrix V is estimated as a sum of two variance components, one here called Q1, modeling the IID part of the signal, where you have equal variance in each direction and no correlation between adjacent time points, and another one, Q2, which is measuring the autocorrelation part, which is modeling the autocorrelation part of the errors. And the two weighting parameters, lambda1 and lambda2, are estimated with a restricted maximum likelihood approach. If you want to account for serial autocorrelations in SPM, you just have to specify the AR1 model in the very bottom. Okay, next problem, multiple comparisons. So when you're running many statistical tests in parallel, as we do, because we are separately estimating and testing for each voxel, as I already said, there will be a large number of spurious findings simply due to the sheer number of tests that you are performing. So the solution here taken would be that instead of controlling the false positive rate per each test, we will control the family-wise error rate across all the tests. So to give you a bit of background for statistical significance testing, the blue curve here, sorry, the bold line here shows us the distribution of the test statistic under the null hypothesis. And our goal is to obtain a critical value above which the area under the curve, or the p-value, is smaller than some significance level, so that we can reject the null hypothesis with some confidence and accept the alternative hypothesis that there is some experimental, some statistical difference between two experimental conditions. So now the problem is that when the null hypothesis, sorry, when the null hypothesis is rejected, if the p-value is smaller than the significance level alpha, then alpha will be the probability of making a false positive result. That is, of rejecting the null hypothesis when it is actually true. Simply because there is a remote possibility that even under the null hypothesis, test statistics are that large. And we have to accept that there is that probability of a false positive result. We cannot let the probability of the false positive result be zero. However, if we are performing a statistical test in one voxel, the probability that we obtain a false positive result is alpha, and the probability of obtaining no false positive result in this one test is 1 minus alpha. If we're then performing a second test in another voxel, the probability of obtaining no false positive result is 1 minus alpha times 1 minus alpha. If we are running a third test in another location in the brain, the probability of obtaining no false positive result will be 1 minus alpha to the power of 3. So we want to here have a look at the family-wise error rate, which is the probability of one or more false positives in n tests. So as this is the probability of not obtaining no false positives, the equation for independent tests is given here. The family-wise error will be 1 minus alpha to the power of n. This curve is showing you this function, the family-wise error, as a function of the number of parallel tests. And you can see that at n equal to 100, this probability is practically 1. Yeah, so we will definitely make a false positive result. And please note that in fMRI, we can have several 10,000 voxels within a single subject brain, which we are testing in parallel. There exists a number of corrections to account for this problem, which mostly consist in adapting the significance level alpha to make it more conservative, if you want. One of them is the well-known Bonferroni correction, which you just divide by the number of statistical tests. Another one is the Shida correction. And although these corrections are very easy to implement, for example, you just have to adjust your significance level, they are also conservative in practice, especially because parallel statistical tests are usually not independent, especially not when this is done across fMRI voxels, because voxels are usually not independent. On the one hand, due to physiology, so there's spatial correlation, adjacent voxels may be sharing some blood flow architecture, and then also due to preprocessing, because we have during preprocessing smoothed our signals, which also makes voxels non-independent. So the solution to this problem in fMRI that is taken is called Gaussian random field theory, or RFT. And since RFT is mathematically and statistically very complex, I'm here trying to explain it in more conceptual terms without giving any equations. So as I already said, the noise is correlated in neighboring voxels, especially due to smoothing, which we have performed during preprocessing. So the idea is to take this dependency between the voxels into account and establish a less conservative criterion than, for example, the Bonferroni correction. And the procedure consists in creating a model of the joint distribution of the noise across all voxels to quantify the voxel dependencies. So what we end up with in the end then is, roughly speaking, that we do not correct alpha, the significance level, for the number of voxels, but we correct it for the number of resolution elements or recells. So because with smoothing, we are decreasing the effective spatial resolution, we have a lower number of resolution elements than we have voxels in the signal. These results are written out into an image called results per voxel .nifty, and the values in this image are used to implement the Gaussian random field theory correction in SPM. So if you want to account for multiple comparisons in SPM, you just have to select FWE correction and pick your p-value and X10 threshold. This is the number of neighboring voxels that have to be activated in order for a cluster to be considered as significant. Here's a comparison of inference corrected and not corrected for multiple comparisons. So on the left, you're seeing uncorrected statistical inference with a p-value of 0.001. And you can see that we are finding very large clusters, some voxels of which may be spurious findings, and which pop out simply due to the large number of voxels that we are testing in parallel. On the right, you see statistical inference whole brain corrected for the family-wise error using a p-value of 0.05. And even although we're using a larger significance level here, 0.05 versus 0.001, we obtain a smaller number of clusters because we have here implemented the correction for multiple testing using random field theory. So I now want to come to aspects of fMRI data analysis which do not really constitute problems, but which rather allow for extensions of the GLM approach to further exciting opportunities. So first, there are parametric modulators, and that is that sometimes there is a triwise variable which is maybe or maybe not influencing the both signal. This can be, for example, stimulus intensity, so the brightness of some visual information showing on the screen, or it can also be a modulator variable determined by the subject, for example, the emotional balance of an image. And the idea here, or the solution, would be to take these modulator variable and use it to create a parametric modulator, which is describing the possible triwise effects and which is added to the design matrix. This usually works in the same way as HF convolution. So we have a stimulus function on the top left and a modulator variable belonging to the same experimental condition. So modulating the activity around the signal elicited by the experimental condition itself. And if we convolve those two functions with the hemodynamic response function, we come up with the onset regressor for this experimental condition and the parametric modulator. We can then assign a weight to both of them and add them up. And this then shows that this parametric modulator allows to increase or decrease activity from the average peak response, here shown in blue, to get a more nuanced response, a more nuanced hemodynamic response to the presented condition and stimulus intensity, for example. In SPM, if you want to implement parametric modulators, you have to implement them, you have to input them along with the names and onsets and durations, which are used to generate the stimulus functions. And the same machinery also gives you the parametric modulator regressors. So if you remember the presentation of the experimental design, I said that all the novel images from encoding are later presented in a retrieval session, and subjects are asked to rate them on a scale ranging from 1 to 5. And we now take these values, 1 to 5, scale them a bit, and add them as a parametric modulator regressor into the design matrix. And this is what actually the second column consists in. So this is a parametric modulator, which is modulating the signal elicited by the novelty condition to possibly account for a variation due to encoding success. So variation due to the subject later remembering or forgetting the stimulus. And if we specify a t-contrast on this parametric modulator regressor and ask whether there is variation related to later retrieval response, we in fact see that there are some regions, including the human hippocampus, which is a brain region thought to be indicative for episodic memory encoding. Okay, the second extension that I want to have a look at is second level GLMs. So usually we don't just want to look for effects in single subjects, but we want to perform, we want to provide evidence for activation differences in some population from which we have sampled the single subjects. That is, we want to find activation differences at the group level, that is, perform multi-subject analysis. And this in fMRI works using the same machinery as before. So we fit a second level model, second level because it's across subjects, over the first level contrast maps, first level because it's obtained from a single subject, to obtain group level statistics. So you can use the GLM to implement a number of designs. You can do one sample t-tests, two sample t-tests, paired t-tests if you have paired observations, a multiple regression analysis where you're looking for covariation with some subject-specific variable, one-way ANOVAs, two-way ANOVAs, and so on and so forth. If you want to run those analyses in SPM, you have to choose the module factorial design specification, and you can then there specify the second level design of the GLM. I have here taken two sample t-tests in order to compare the brain activation due to subsequent memory, which which I showed you in the first extension, and compare that between young subjects aged 18 to 35 and older subjects aged 60 plus. And what we then see is that there are differences regarding this response in a large number of regions, consisting one of those in the human memory networks, running from temporal over occipital into parietal areas, and that we have differences regarding this contrast in default mode regions, such as the precuneus and the temporal parietal junction. So this is it for general linear model analysis. And I now want to highlight two further possibilities which can be enabled by this GLM approach. So in our general linear models, we typically use condition-wise regressors. That is, we are collecting all the trials from one experimental condition into a single regressor. And what you could also do instead is to specify a trial-wise design matrix in which not every condition, but every trial has their own HRF convolved regressor. This then could look like this. And this allows you to estimate trial-wise response amplitudes. However, these trial-wise response amplitudes tend to be correlated because the hemodynamic response is very slow. And as you can see here from the design matrix, this causes the trial-wise regressors from adjacent trials to overlap with each other, which then induces correlations into our estimates of the trial-wise response. This is a well-described problem, and one way to account for that would be to estimate the trial-wise responses and then describe a new model which accounts for the trial-by-trial correlations, which by using the trial-by-trial covariance matrix, which is just a function of the trial-wise design matrix, as is shown here in this equation. Another extension of the GLM approach is multivoxel pattern analysis. So once that you have obtained trial-wise estimates of the response amplitude or run-wise estimates of the response amplitude, you can ask yourself, do these estimates allow to distinguish experimental conditions from each other? So you can run a machine learning-based decoding analysis in which you take the activation patterns from two experimental conditions. This is shown here in panel C. And these activation patterns can be from a number of trials or from a number of runs. And then you can plot them in your multidimensional space. Here we're just looking at two voxels and see whether one can draw a plane or a hyperplane in hyperdimensional space in order to separate these two conditions from each other based on their activation patterns. And if this is the case, this would allow you to conclude that the brain region consisting of those voxels carries information about the difference between the experimental conditions. So this all belongs to the large area of multivoxel pattern analysis, about which there will be another session in this neuroimaging lecture. So at the very end, I want to wrap up with a summary of fMRI data analysis, but only restricted to what I have now presented in the previous and this session. So we take our measured fMRI scans and enter them into slice timing in order to correct for acquisition time, enter them into realignment in order to correct for head motion. From spatial realignment, we also get the head motion parameters, translations and rotations, and we get the mean functional MRI image. We then take our structural MRI scan and enter it into co-registration, co-register it to the mean functional image, and segment it into tissue types using tissue probability priors. This gives us deformation fields, which we can then use to normalize the realigned functional scans. Finally, functional MRI images are smoothed using a Gaussian kernel, and this concludes pre-processing. The pre-processed fMRI scans are then taken for model specification, which consists of a design matrix, which includes knowledge about the experimental conditions and what has happened during the experiment, and B, nuisance variables such as the head motion parameters. This statistical model is then estimated, which gives us beta images quantifying the influence that experimental conditions have on signal, as well as estimates of the residual variance. And from beta images, we can calculate contrast images, and the contrast images together with the residual variance enter statistical inference, which allows us to obtain thresholded statistical parametric maps from which we can make conclusions about the association of brain areas and cognitive function. This concludes statistical analysis. So with that, I want to say thank you and goodbye.